Hey guys, so the last part of the atom is us talking about isotopes, and you guys looked at isotopes a little bit when you did your web quest the other day. So the definition of an isotope is when atoms have the same, they're of the same element, but they have different masses. So same element, which means the atomic number has to be the same, but they have different masses. Now, even though this is a perfectly good definition, when there's multiple ways to answer a question in a short response type of question, the regents will usually specify how they want you to answer it. So for an isotope kind of question, usually it says in terms of subatomic particles, which means even though this is a perfectly good definition, if you don't talk about protons, neutrons, electrons in your answer, you don't get credit. So just so that we have it in our notes, we want to think about what subatomic particle makes the atoms the same element, what makes them have the same atomic number. So it's that they have the same protons. The protons are not allowed to change. But what can make one atom heavier than another is making the number of neutrons different. So that's just like a more specific definition. Okay, so in the examples below, guys, we're going to look at different ways to represent an isotope. So here for number one, we have oxygen dash 18. So when you see a dash with a number written after the element name, that number represents the mass. Okay, so if you guys, you actually still need your periodic table. We still get the number of protons from the atomic number. So if you guys can find oxygen on the periodic table, tell me what atomic number it is. That's going to be how many protons it has. So the atomic number is 8. Now, isotopes, even though the masses can be different, they're still atoms. They still are neutral. They don't have a positive or a negative charge. So if I have 8 positive protons in this atom, I need 8 negative electrons to cancel them out. The only time the electrons are going to be different from the protons is if you have an ion, if you have a little charge, which here we don't see that. All right, so now the neutrons, here's where you have to be careful. So neutrons is mass minus atomic number. So if you say, oh, this is oxygen, and you go right to the periodic table, you would say, oh, okay, well, 16 minus 8 is 8. Here they're giving you a different mass. They're telling you that some of the oxygen atoms in the world have a mass of 18, and this particular one does, and that's the mass you have to use. So when you do 18 minus 8, you get 10. So this is an isotope of oxygen. It has a different mass than what's on the periodic table because it has a different number of neutrons. It's a little bit heavier. All right. So this is another way. Number 2 is another way of showing isotopic notation. So you're given the symbol and you're given these 2 numbers on the left-hand side. Now this is confusing because the Regents reference table is actually labeled this way. The top number is the mass, and the bottom number is the atomic number. But if you look at your reference tables for honors, they do it the opposite. They put the atomic number on the top and the mass number on the bottom. So for the Regents, guys, this is actually labeled, so you'll be able to look and say, okay, the mass is on the top. But looking at your periodic table, it's opposite. So it makes sense, though, when you're given 2 numbers, the higher number is the mass because the higher number is what's made of the protons and neutrons. Okay, the atomic number is just the proton, so it's always going to be lower than the mass. So that's if you forget. So again, guys, if you look on the periodic table, copper's mass is closer to 64, but here they're giving us a mass of 65, so that's the mass we have to use. So protons, I don't even have to go to the periodic table here because they're giving me the mass and the atomic number. So the atomic number is 29. The electrons then have to also be 29 to keep it neutral. But now when I'm figuring out neutrons, I have to do 65 minus 29 instead of 64 minus 29. And I get 36. Okay. Last thing they can do, guys. So this potassium example is different from copper in that they just write the mass and there's no atomic number written on the bottom. And they can do that because you can still go to your periodic table and get the atomic number of potassium. So it has an atomic number of 19, which means it has 19 protons and electrons. But now instead of 39 minus 19, we want to do 41 minus 19. So this isotope of potassium has 22 neutrons. All right. So that's isotopes. Now, how might you see this on the regions? So this multiple choice question is asking us which elements are isotopes, and notice that they give us the symbol with the two numbers on the left side. So the masses need to be different. The top numbers need to be different, and the bottom numbers need to be the same atomic number. So can 1 be an answer choice? No. Number 2 can't work either because the masses are the same. All right. If we look at number 3, those are just two totally different elements. They're X and Y. Atomic numbers are different, masses are different, everything is different. Okay. Here we have 65 and 66, different masses, but same atomic number, so the same symbol. So those would be isotopes. Here's that question that I was talking about, explaining in terms of subatomic particles why they're isotopes. So that means you can't say they're the same element with a different mass. You have to talk about what particles make them the same element. So they have the same protons, different neutrons. Okay. All right. So guys, there's actually a difference between atomic mass, which is the number for the mass that's on the periodic table, and mass number. If I give you an atom, right, and I ask you what the mass of the atom is, you would add up the protons and neutrons. You don't get a decimal for your answer, you get a whole number. So for example, like chlorine, right? If it has 17 protons and 18 neutrons, its mass number should be 35. So if you look at chlorine on the periodic table, why is the atomic mass this weird long decimal number? The atomic masses on the periodic table are actually calculated masses. So let's write the definition of atomic mass and then we'll look at how they're calculated. So average atomic mass is the weighted average of the elements naturally occurring isotopes. So guys, what's important here is that word weighted. Okay, that means like you might be graded in some of your classes. You might have like a weighted average, meaning like tests are worth 60% of your grade for the quarter and homeworks are only worth 10%. So when a test grade goes into the portal, it's going to make your average go up or down more than if I were to put a homework grade in the portal. That's what it means to be weighted. Certain grades are worth more than others. So with isotopes, the average is weighted. So for example, let's look at this. All right, so hydrogen. In nature, there are two isotopes of hydrogen. Some hydrogens have a mass of 1, that's the purple, and some hydrogens have a mass of 2, that's the green. You guys are definitely going to need your calculator, so if you want to pause and go get it now, you'll just have it for later. But if I find the average, 1 plus 2 is 3, and if I do 3 divided by 2, I should get 1.5. I should get a number right in the middle between 1 and 2, right? But if you guys look on the periodic table at the average atomic mass of hydrogen, it's much closer to 1. The average between these two isotopes is like 1.00 something, right? Because look at the abundance of hydrogen 1 and 2 in nature. Look at all those purple dots and look at that green dot. 99.9885% of the hydrogen found in nature has a mass of 1. So when you find the average is going to end up being a lot closer to 1. It's not right in the middle because it's a weighted average. The percentage of it that exists matters. Okay? So hydrogen only has 2 isotopes. Let's look at magnesium. Magnesium has 3 isotopes, 24, 25, and 26. What color dot do you see more of on the screen? You see more purple, right? If you guys go and look at the atomic mass of magnesium on the periodic table, it's closer to 24 than to 25 or 26. That's because there's more magnesium 24 in nature. So those numbers on the periodic table, those come from calculating the average of all the isotopes that exist, but it's weighted. It depends on how much of them exist in nature. So chlorine is the example that we're actually going to do together. And chlorine has 2 isotopes, 35 and 37. And if you look, there's more 35 in nature than 37. So if you guys had to take a guess as to what the atomic mass of chlorine will be closer to, I hope you would guess that it would be closer to 35 because there's more of it in nature. So let's take a look at how we do this. We're going to take the mass of the isotope and multiply it by its percent abundance. So 35 times 75.78. Then we're going to add it to the next isotope times its percent abundance. 37 times 24.22. Then to get rid of those percents, we're going to divide the whole thing by 100. Okay, so guys, if you're using your phone for the calculator, that's going to be annoying. You want to use a calculator where you're able to put in parentheses where you need them. I would do the top row first and then hit equals and then divide by 100. Otherwise, your calculator might do PEMDAS in the wrong order, which you don't want it to do. All right, so when you throw that in your calculator, you get 35.4844. So we don't want to round out average atomic masses. If you look on the periodic table, they are not rounded. They have quite a few numbers after the decimal place. So were we right that the average is closer to 35 than it is to 37? Yes, because there's more chlorine 35s in nature. Okay. Another way you could write this, guys, and this is totally based on your preference. If you want to move the decimal over 2 spaces in the percent, then you don't have to divide by 100 at the end because you kind of already did it. So whichever way you like it better, just make sure you don't do both. Okay. Last thing to talk about, the units for average atomic mass. So our units are going to be AMUs, atomic mass units. The definition of an AMU, 1 AMU is equal to 1/12 of a carbon atom. So carbon has a mass of 12. So 1/12 of it would be a mass of 1. So that's what they use to come up with the scale for this unit for mass. We're not going to be using grams because atoms are too small to measure in grams. Okay, so that's it with the average atomic mass. That is a formula that you need to know. And I'll give you some practice questions and then we'll look at this more again tomorrow.